Hey everyone, ever imagine like a computer helping your doctor, figure out a diagnosis?
Hmm.
I mean, it might sound kind of sci-fi,
Yeah.
but it's actually getting closer to reality than you think. And so today on our deep dive, we're going to be diving into how something called logistic regression
Right.
is being used to detect breast cancer.
Wow.
So we've got some pretty technical material for this deep dive,
Okay.
using Python code as our main source. But
Mm.
don't worry, we're not going to like bore you with all the,
Uh-uh.
lines of code and stuff like that.
More about the concepts,
Yeah, no,
not becoming
it's
programmers.
yeah, exactly. We're going to break down the ideas in a way that makes sense.
Right.
Especially we were thinking, for you out there listening,
Yeah.
um, you know,
Like, how would this apply?
yeah, like imagine having a second opinion,
Yeah.
but one that's based purely on data.
Hmm.
That's kind of the potential here. So
Wow.
buckle up because we're going to uncover how this machine learns from medical images,
Okay.
how reliable it can be.
Uh-huh.
And we'll even compare it to what doctors use in their practice today.
Yeah, like what's the difference? Think of
Yeah.
it like peeking behind the curtain
Yeah.
to see the technology that's shaping the future of medicine.
Okay, let's start with this whole logistic regression thing.
Right.
Imagine you're a doctor and you're looking at a mammogram
Okay.
and you're trying to figure out if a tumor is cancerous or not.
Yeah.
It's a tough call, right?
Oh, yeah.
Logistic regression can help by analyzing like tons of features in the image
Yeah.
and then calculating the probability, the chance that it's malignant.
So it's like having this superpowered assistant crunching the numbers
Yeah.
and giving you this percentage to make that decision a little less stressful.
So instead of just relying on the image,
Right.
doctors would have like this extra piece of information.
Exactly.
That's pretty cool.
Yeah.
But how does the machine even learn to do this?
Right.
It's not like it went to med school.
That's where the learning part comes in.
Okay.
It's trained on tons of previous cases, some with cancer and some without,
Ah.
and it learns to spot those subtle patterns that might be tough for the human eye to catch.
So after studying all those examples,
Yeah,
it's kind of like the machine becomes a detective.
that's a great way to put it.
It learns to spot the clues.
Yeah,
But instead of shouting guilty or not guilty, like in a courtroom,
right.
it gives you a probability score, like saying 80% chance this is a problem.
Yeah, like building a case weighing the evidence based
Right.
on what it's learned from past data, and then we can decide how to act on that probability score.
And our source material mentions the code uses 1 for malignant
Right.
and 0 for benign.
Yeah.
That's interesting. So they're basically speaking in code
Well,
using numbers instead of words.
not exactly thinking like that, but it's how we represent those categories in a way the computer can process. Think of it like translating medical terms into a language the computer understands.
Ah, so it's all about making the data like digestible for the computer.
Exactly.
Speaking of data, what kind of information are we feeding
Right.
this machine learning model?
Yeah.
Is it just the mammogram image or is there something more?
So our source material describes using a data set with 33 different features,
Okay.
all extracted from those medical images.
Wow, 33.
Think things like the size of the tumor, its shape, even its texture,
Okay.
all sorts of factors that could be relevant.
So it's not just looking at the image as a whole,
Right.
but it's breaking it down into
Breaking it
all
down.
these tiny details.
Exactly. And that's one of the things that makes machine learning so powerful.
Yeah.
It can consider all these features simultaneously,
Right.
something that would be incredibly difficult for a human to do.
Yeah. I can barely remember a grocery list,
Uh-huh.
let alone 33 details about a tumor. But I guess that's why we have these powerful computers to help us out.
But even with all this data,
Yeah.
quality is key.
Okay.
If the information isn't accurate or relevant,
Yeah.
even the best algorithm won't be able to do much with it.
So it's kind of like you can have the best chef in the world,
Right.
but if the ingredients are bad,
Yeah.
the meal won't be any good.
A perfect analogy.
Okay.
Our source material even highlights how they had to drop a couple of columns from their data set.
Okay.
An ID column and another unnamed one because they weren't relevant to the diagnosis.
That makes sense.
Yeah.
You wouldn't want something like a patient's ID number
Right.
influencing whether or not they have cancer.
Exactly. And there's also a diagnosis column
Okay.
that originally used M for malignant and B for benign,
Uh-huh.
but the code translated those letters into the 1 and 0 system we talked about earlier.
So it's all about making sure the computer has the right information
Yeah.
in the right format.
Yeah.
It's fascinating how much goes into preparing the data,
Right.
even before the learning even begins.
It's like Building a house, you wouldn't start constructing the walls before you lay solid foundation.
Yeah.
Data pre-processing is that foundation in machine learning.
Ah, so that's what pre-processing is all about, getting the data ready for its big debut, so to speak.
Exactly. And one key step in this process is something called normalization.
Okay.
It sounds a bit intimidating,
Uh-huh.
but think of it like this.
Yeah.
You have a bunch of ingredients for a recipe,
Yeah.
but they're all in different units, grams, teaspoons, cups.
Right.
Normalization is like converting everything into the same unit so you can easily compare and use them together.
So it's about putting everything on the same scale.
Right.
So no single feature outweighs the others
Exactly.
just because it happens to have larger numbers.
Yeah,
Like making sure a teaspoon of salt doesn't somehow overpower a cup of flour.
precisely. It ensures that all features have a fair chance to contribute to the model's learning process.
Okay, so we've got our data all cleaned up and ready to go.
All right.
What happens next?
So the next step is to split the data into what we call training and testing sets.
Okay.
It's like studying for a test
Yeah.
and then taking a practice exam to see how well you've learned the material.
So we're basically giving the model a chance to practice on one set of data
Exactly.
and then see how well it performs on a completely new set it hasn't seen before.
In this case, they used 85% of the data for training
Okay.
and 15% for testing.
So the model gets to practice on the majority of the data,
Right.
and then we evaluate it on the remaining portion to see how well it generalizes to new information.
That's right. It's all about making sure the model can apply what it's learned
Okay.
to real-world situations. Now, once the data is split, the fun part begins, building the actual model.
Now, this is where it gets really interesting, right? This is where the machine learning magic happens.
Indeed, but it can get a bit technical, so let's try to keep it simple.
Okay.
The first step is initializing weights and bias.
Okay.
Imagine these as starting points for the model's learning journey,
Okay.
like setting the stage for the model to start making connections.
So it's like giving the model a little nudge in the right direction,
In a way, yes.
a head start on its learning adventure.
These weights and biases are like the knobs and dials the model can adjust
Okay.
as it learns from the data. They determine how much influence each feature has
Uh-huh.
on the final prediction.
Yeah, so it's like fine-tuning the model,
Exactly.
tweaking those settings to make it more accurate.
And to help with this fine-tuning,
Okay.
we use something called the sigmoid function. I know it sounds a bit complicated.
I love learning new things, even if they sound a bit intimidating at first.
Well, you're in for a treat then. The sigmoid function takes all those complex calculations the model makes
Okay.
and transforms them into something we can easily understand. Probabilities.
So it's like translating from computer speak into human speak. It's turning numbers into percentages that tell us the chance of something happening.
Instead of just getting a bunch of numbers,
Okay.
we get a clear output. Like, this tumor has a 75% chance of being malignant.
Yeah.
And that's where the real power of logistic regression lies.
Yeah.
It gives us a way to quantify uncertainty.
I see. So it's not just a black and white answer.
Right.
It's about understanding the level of risk,
Yeah.
the likelihood of a particular outcome.
Exactly.
But how does the model actually learn from the data? How does it adjust those weights and biases to improve its accuracy?
That's where the concept of forward and backward propagation comes in.
Okay.
Think of it like learning to ride a bike.
Okay.
You don't just hop on and start pedaling perfectly right.
Oh, I definitely remember those early days of quick knees and bruised elbows.
So the model goes through a similar process.
Yeah.
In forward propagation, it makes a prediction based on its current settings, those weights and biases we talked about.
Yeah.
It's like taking the bike for a spin. Then, in backward propagation, it compares its prediction to the actual result, like noticing you veered off course or wobbled a bit.
Yeah.
And based on that feedback, it adjusts its settings, those weights and biases, to improve for the next try.
So it's like the model is constantly learning from its mistakes.
Exactly. It's a continuous process of trial and error,
Okay.
refinement and improvement.
Yeah.
And the beauty of it all is that it happens automatically without us having to manually adjust anything.
That's amazing. So the model is iteratively learning,
Right.
kind of like practicing a skill over and over until it becomes more proficient.
Yeah.
Our source even mentions a code snippet
Oh, yeah.
that says, cost after iteration I.
Right.
What does that mean exactly?
Ah, good eye. That snippet is like a progress report
Okay.
showing how the model is improving over time.
Okay.
Cost refers to the error in the model's predictions.
Uh-huh.
So as the model goes through more iterations, more rounds of learning,
Okay.
the cost should decrease,
Uh-huh.
indicating that it's getting better at making accurate
So
predictions.
it's like watching the model score improve with each practice round.
Exactly.
But how do we actually know if the model is performing well? How do we measure its accuracy?
That's a great question, and it brings us to the crucial step of evaluating our model.
Okay, so we've built this model,
Right.
we've trained it on all this data,
Yeah.
and now it's time to put it to the test.
Yes.
See how well it actually performs in the real world.
Precisely. And that's where we'll pick up in the next part of our deep dive.
Totally.
We'll explore how this model performed in detecting breast cancer,
Right.
and maybe even challenge ourselves a bit to see if we can understand its inner workings.
Okay.
Are you ready to see how our machine learning detective stacks up?
You bet I am. This is getting more fascinating by the minute.
See you in part 2.
All right, see you then. Welcome back. Before the break, we were just getting to the exciting part, finding out how well our DIY logistic regression model actually does at detecting breast cancer.
Yeah, it's like waiting for the results after a big exam, right?
Right.
All that studying, and now it's time to see if it take off.
Exactly. So spill the beans.
Yeah.
What did our source material reveal about the model's performance?
Well, drumroll, please. The model achieved an accuracy of about 80.75% on the training data.
80.75%. So that means it got about 8 out of 10 cases right. Not too shabby for a model we built from scratch. But wait, there's more, right? What about the test data, the one the model hadn't seen before?
Ah, yes, the true test. On the test data, it achieved an accuracy of around 81.39%.
Wow, so it actually did slightly better on the new data. That's
Yeah.
impressive. But before we get too excited, I have to ask, is 80-something% really good enough when we're talking about something as serious as cancer detection?
That's the million-dollar question, isn't it? While these numbers might sound good in other contexts when it comes to healthcare, we want to aim for the highest accuracy possible. After all, we're dealing with people's lives here.
I hear you. So where does this leave us? Is our model ready to be used in hospitals?
Not quite yet. It's a promising start, a solid foundation, but there's still work to be done. Remember, the human body is incredibly complex, and there's a lot of variation between individuals.
Right, it's not like every case of breast cancer is exactly the same.
Exactly. So while 80% accuracy is a good starting point, we need to keep pushing for improvement.
So how do we do that? How do we make our model even better at detecting cancer?
That's where things get really interesting. Researchers are constantly exploring ways to enhance these models using more sophisticated techniques and incorporating even more data.
More data. Like what?
Well, think about all the information doctors consider when making a diagnosis, a patient's medical history, family history, lifestyle factors, genetic information. All of this could potentially be incorporated into the model to give it a more holistic view.
So it's not just about the image itself, but about understanding the individual patient as a whole. That makes a lot of sense. But hold on, I have another question. You mentioned before that doctors use mammograms to detect breast cancer. How does our fancy model compare to this tried and true method?
That's a great question. Mammography has been the gold standard for breast cancer screening for many years, and for good reason. It's a relatively safe and effective way to detect cancer early when it's most treatable.
So it's like a baseline, a benchmark for our model to compare against.
Exactly. But even mammograms have their limitations. Sometimes they can miss cancers, especially in women with dense breast tissue. And sometimes they can flag something that looks suspicious but turns out to be benign.
Ah, so there's a chance for both false negatives and false positives. That sounds stressful for patients.
It can be, and that's where machine learning comes in. Researchers are exploring ways to use these algorithms to analyze mammograms, looking for those subtle patterns that might be difficult for even the most experienced radiologist to spot.
So it's like having a second set of eyes, one that's trained on thousands, maybe even millions of images, and can pick up on those tiny details that might be missed by the human eye.
Exactly. And not only that, it can help radiologists prioritize cases, flagging those that are more likely to be cancerous for further review.
That sounds like a game changer. It could potentially save lives by catching cancers earlier and reducing unnecessary biopsies.
That's the hope. But as with any new technology, we need to be cautious and make sure these models are thoroughly tested and validated before they're used in clinical practice.
Right, it's about finding that sweet spot, that balance between the power of technology and the expertise of human doctors. But I'm curious, our source material also experimented with something called scikit-learn. What's that all about?
Ah, scikit-learn. It's a fantastic tool, like a Swiss Army knife for machine learning. Think of it as a library of pre-built models and algorithms, including, you guessed it, logistic regression.
So it's like having a toolbox full of ready-made solutions, as opposed to building everything from scratch like we did with our model.
Exactly. It's a great way to check your work to see how your custom model compares to those that have been optimized and refined by experts.
So how did our little DIY model stack up against the one from Scikit-learn? Was it a David versus Goliath situation?
Well, not quite. Our model held its own, achieving those 80-something% accuracy scores we talked about. But the scikit-learn model did outperform it slightly with around 86.33% accuracy on the training data and 89.53% on the test data.
So the pre-built model edged us out, but not by a huge margin. I guess there's something to be said for building things from scratch, even if it's not always the most efficient approach.
Absolutely. Building from scratch gives you a deeper understanding of the underlying concepts, the nuts and bolts of how these algorithms work. It's like learning to cook from scratch before using a microwave. You appreciate the process more, you understand the ingredients better.
I love that analogy. So while scikit-learn might be the faster and more efficient option, building our own model gave us a much richer learning experience.
Precisely. And it also highlights the trade-offs involved in any machine learning project. Sometimes you need to prioritize speed and efficiency, while other times a deeper understanding of the process might be more valuable.
Okay, so we've explored the world of logistic regression.
Yeah.
We've built our own model, we've compared it to a pre-built one, and we've even seen how it stacks up against traditional methods like mammography. It's been quite a journey. But before we wrap up this part of our deep dive, I want to bring it back to you, the listener. What stands out to you from all this?
What has you most intrigued or surprised about the potential of machine learning in healthcare?
Let us know your thoughts, because in the final part of this deep dive, we'll explore the bigger picture, the potential impact of AI on the future of medicine. Stay tuned. Welcome back to our deep dive into the world of machine learning and breast cancer detection. So you've heard us talk about, the nuts and bolts of logistic regression, how we built a model from scratch, and even how it compares to the tools doctors use today.
Right.
But now it's time to kind of like zoom out a bit and think about the bigger picture.
The bigger picture, exactly.
We've been, focused on this specific example, but like, what does all of this mean for the future of healthcare?
Well, what's fascinating to me is how this example kind of opens the door to so many possibilities.
Yeah.
Imagine a world where AI helps personalize your treatment,
Okay.
tailoring it precisely to your genes,
Wow.
your lifestyle, and medical history.
Personalized medicine. That sounds incredibly futuristic.
It might sound like science fiction,
Yeah.
but it's closer than you think. We're already seeing glimpses of it with things like targeted therapies and precision medicine.
So using data and algorithms to figure out the best treatment plan for each individual patient.
Exactly.
It's amazing.
It is, and the potential benefits are enormous.
Yeah?
Think about it, instead of a one-size-fits-all approach,
Right.
you'd have a treatment plan that's specifically designed for you,
Wow.
increasing the chances of success and reducing the risk of side effects.
That's incredible. It feels like we're on the verge of like a healthcare revolution.
We are, and machine learning is playing a key role.
Yeah.
But of course, with any new technology, there are challenges and considerations.
Absolutely. And earlier we talked about the importance of data quality
Right.
and how even the best algorithms are only as good as the information they're fed.
Right, and as we move towards more personalized medicine, data privacy becomes even more crucial.
Yeah.
We need to ensure that sensitive medical information is protected and used responsibly.
That's a great point. It's not just about the technology itself, but about building trust and ensuring ethical use.
Exactly. And as these technologies continue to evolve, we need to have open and honest conversations about their implications,
Yeah.
both the benefits and the risks.
So can machines learn to diagnose? I think our deep dive into logistic regression and breast cancer detection suggests a resounding maybe.
A maybe with immense potential and a future that's still being written.
We've seen that logistic regression, while sounding complex, is actually a pretty intuitive way for a machine to learn and make predictions. And while it's not a crystal ball, it can offer valuable insights, potentially helping doctors make more informed decisions.
And who knows what the future holds? As these technologies advance, we might see even more sophisticated algorithms that can analyze even more data, leading to even more accurate and personalized diagnoses.
It's exciting to think about. Now, before we sign off, we want to leave you with one final thought to ponder. If you were designing a medical AI, what factors beyond accuracy would you prioritize?
What would make you feel comfortable and confident trusting a machine with your health?
It's a question worth considering as we enter this new era of AI-powered healthcare. Thanks for joining us on this deep dive. We hope you've learned something new and maybe even feel inspired to explore this fascinating field further. Until next time, keep learning, keep questioning, and keep diving deep.